Uncountable sets. This video is a continuation of our previous video on cardinality of a set, where we focused mostly on the countable case. Here we look at Cantor's landmark theorem. The set of real numbers is uncountable. There are too many real numbers to be able to fit them all into a list, meaning that there is no infinite sequence that includes every real number. We already know that the set of natural numbers has cardinality less than or equal to the set of reals. So to show the result, we just have to show that this inequality is strict. In other words, there's no bijection. And the proof now is by contradiction. Suppose, on the contrary, that the set of real numbers is countable, then the open interval 0, 1 must also be countable, right? I mean, any subset of a countable set is also countable. Actually, the interval 0, 1 has the same cardinality as the reals anyway. So the real numbers between 0 and 1 can be listed in a sequence A1, A2, A3, and so on. Of course, this list would have to be infinite. And here's one of the few times when I can think of that decimal representations are actually useful for something, for proving a theorem about the real numbers. Each real number ai in our list has a decimal expansion. As shown, the jth digit of ai I will call aij. So ai expands with digits ai1, ai2, ai3, and so on, each digit being in the range 0, 1, 2, 3 up to 9. Now, we've talked about decimal expansions before, and the fact that decimal expansions are not unique in general, but this issue will not actually become a problem for us in this proof. I'll point out at a later point why that is, why it doesn't matter. Here, I have listed the numbers between 0 and 1, and they're in a vertical list, A1, A2, A3, and so on, reading top to bottom. In the horizontal direction, I've expanded each of our numbers in a decimal expansion. This is now looking like a table extending infinitely far, both downwards and to the right. But each row is a single number, with the decimal digits listed across from the left column off toward the right. This list is supposed to contain every real number between 0 and 1. So to get a contradiction, we just need to show that there is some number between 0 and 1 that is not already in this list. Can we do that? So the trick is to look at this diagonal, where I've highlighted the jth digit of the jth number for each j. Like staring at the diagonal of a matrix, except in our case, an infinitely long diagonal. The number that gives us a contradiction will have to be a number b, whose decimal digits b1, b2, b3, and so on have the property that each digit bj is different from ajj. So if you have a number b whose jth digit differs from the jth diagonal digit in this list, then that's going to be a number which is not anywhere in our list, and that will be our contradiction. But of course, there are many ways to do this. We would like to give a definite formula for bj. One way to do this is to choose bj to equal 3 unless ajj is 3, in which case choose bj to be 7. So I'm going to end up with this number whose decimal expansion has only 3s and 7s, but it's a way of making sure that the number is nowhere in our list because it'll differ from each number in the list by looking at this particular digit. So it cannot be the jth number in the list for any j. This argument is known as Cantor's diagonal trick. The name is self-explanatory. Like any good trick, this is an idea that, far from being a one-off trick, it has become a standard argument for proving a huge number of theorems. What seems like a trick the first time you see it Once mastered, this becomes a technique and a tool of the trade. Now let me comment here on the 3s and 7s. I could have replaced them by 1s and 6s, say, but I was very intentional not to choose 0s or 9s. I want to avoid 0s and 9s because of the fact that if you had a number b with a bunch of 0s and 9s, then you start to worry that this could be a number that could be represented as a decimal in more than one way. And then you'd worry, is this actually in our list at all? It might look different, but having a different decimal expansion might nevertheless give you the same number. As it is, the way I came up with my number b, having digits 3s and 7s, this is an example of a number that has a unique decimal expansion. So it cannot be anything in the list if it differs from each number in the list in some decimal place. That's why I chose 3s and 7s. And the point about having a definite formula rather than just say, in each digit, pick something that's different from the diagonal, that would leave you to possibly have to rely on the axiom of choice. I don't want to do that. I want to have something really constructive for my number b so that somebody cannot criticize me for having to use the axiom of choice. This proof holds in ZF. There's no axiom of choice required. And as proofs go, it's pretty elementary. Nevertheless, it is unsettling the first time a student sees it. It's one of those things that precipitates arguments with some students. But if you have qualms about this proof, don't be afraid to talk to me. It's a really important argument because it does occur as a technique that is used in other proofs as well. All right, moving on to applications. I first mentioned that this gives us a proof of the existence of transcendental numbers. These are the numbers which are not roots of any non-zero polynomial with rational coefficients. Every real number, just as well complex numbers, either algebraic or transcendental. Algebraic numbers are those which are roots of non-zero polynomial with rational coefficients, and everything else is transcendental. So the algebraic numbers include the rational numbers and much more. Numbers like square root of 2. Square root of 2 is algebraic. The number I is algebraic. What's an example of something transcendental? Well, pi is transcendental and e is transcendental, but those are much harder to prove. This gives us an easy proof of the existence of transcendentals. The theorem is that there are transcendental numbers in the complexes, but also in the reals. And the proof is easy. The algebraic numbers, as we pointed out in the previous video, form a countable subset of the reals. That cannot be all of the reals because the reals is uncountable. So it has to be a proper subset. So it's an example of what we call a non-constructive proof. It's non-constructive in that it proves the existence of something without actually giving you a single example. Actually, by the cardinality argument, almost all reals are transcendental. But actually finding one and knowing for sure that it's transcendental is very tricky. We do know that pi is transcendental, e is transcendental, but these facts are very hard to prove. Very hard. Well, so I have proved both of those in a graduate level class, but they each took me 2 or 3 classes, and they were pretty technical. Now, the first proof of an explicit transcendental number was given by Joseph Liouville in 1844, which was the year before Cantor was born. Now, the cardinality argument, which came later, thanks to Cantor, was non-constructive but much more elementary. So, by the way, this kind of cardinality argument can prove the existence of lots of things. For example, it gives you a quick proof that there exist lots of irrational numbers. In fact, most real numbers are irrational. But that's not so impressive because we already have a pretty easy proof that square root of 2 is irrational. Okay, so E is the irrational. That takes a couple of minutes to prove. Proving that pi is irrational, I can do that easily within one lecture at the undergraduate level. And I'm not giving you the proof here. Giving non-constructive proofs is good application. We're ready to talk about the hierarchy of sets from the perspective of their size, their cardinality, starting at the bottom with the finite sets. Just above that on the ladder, we have our countably infinite sets. These are the sets like the natural numbers, integers, rationals, n-tuples of rationals, the algebraic numbers, things like that. That's just one rung on the ladder above finite. Above that, we have sets like the reals. The set of reals is on a strictly higher level as far as cardinality is concerned. Other sets having the same cardinality as the reals, they would include complex numbers, real n-space, etc. The cardinality of each of these sets is usually referred to as the cardinality of the continuum. It's a very good name for it. And then you can go above that to still larger sets. What's an example of a set that's larger than the set of real numbers? Well, if you take the set of all functions from the reals to the reals, think about all the graphs you can draw in the plane. That's a strictly larger collection, a strictly larger set. And, of course, we'll be talking a lot about members of this collection, real valued functions from R to R. So what analysis is largely concerned with. This hierarchy goes up and up forever. There's no limit. There's, in fact, no largest set. Whatever set you find, rest assured that there are still much, much larger sets than that. This is an infinite hierarchy. Okay, we're saying that there are not only many levels of infinity, there are actually an infinite number of different levels of infinity. Everything from the reals on up is uncountable. But as uncountable sets go, the set of reals, okay, it's big, but it's still pretty small as infinity goes. So it's puny. And what about the set of integers or rational numbers? Well, that's just, that's still really incredibly small sets you're talking about. It's just barely infinite. By the way, every time I'm referring to infinite here, I'm referring to sets having infinite cardinality. So one of the major confusions people have when talking about infinity is the tendency to mishmash the different notions together in their head. People do this with concepts all the time, and particularly with infinity. If you do this, confusion in your head with the word infinity, you get all twisted in knots. There's not just one notion of infinity for mathematicians. There are many, many different senses of the word infinity. So you have to be careful to be precise. Here we're just talking about infinite cardinality of sets. The lazy 8 symbol from calculus is not about this. It's a very different use of the term. When we write down the lazy 8 symbol for limits, we're not talking about infinite sets. We're not even talking about infinite values of anything. Everything is finite. It's just a symbol that is a shorthand for some other kind of statement that takes some quantifiers to fully explain. And in calculus, we had a plus infinity and a minus infinity, which were different notions. But when we're talking about cardinality of sets, there's nothing like minus infinite cardinality of a set. Of course, we're talking about different things. Be careful of the terminology. In set theory, we have an infinite cardinality of cardinal numbers. We also have an infinite hierarchy of something called ordinal numbers, which is another way of looking at infinite numbers. And I can think of many other meanings of infinite, different from cardinality that we're talking about here. The point where people start getting confused is when they naively take one idea out of context, stick it in another place, without realizing that the words have different meaning. Now let's look a little more closely at this hierarchy to see if we have actually skipped anything in between these levels. Well, between the finite and the countably infinite, there's nothing there. There's just a jump from finite to countably infinite. There's nothing in between. So countably infinite is just barely infinite. Then there's a gap between countably infinite and the continuum. Now the question is, are there any sets lying in this gap? Is there a set that is bigger than the integers but smaller than the real numbers? Or how about the next gap between the set of real numbers and the set of functions from reals to reals? These questions about the gaps was an open problem until the middle of the 20th century. It was at the time one of the reigning problems of mathematics, one of the most famous open problems. And since the work of Paul Cohen in 1960 or so, combined with earlier work of Kurt Gödel, we now know that this is one of those questions that cannot be resolved by our popular axiom systems, ZF and ZFC. There's really no absolute answer here. Just isn't an answer. The apparent universality of the question is actually an illusion. There's actually no way to prove or disprove the existence of sets that are in these gaps, having intermediate cardinality, if you're going to just use the ZFC axioms. If you want an answer, then you're free to say yes or no, depending on your personal preference, and to make that statement a new axiom, if you like, and start doing some new kind of mathematics. People do that. And then they go on to develop more mathematics. And we're still talking about games here. There's no right or wrong choice of axioms. Sorry if I'm shattering your perceptions about what universality means in mathematics. But fortunately, as I've said before, resolving the gap about the continuum does not have any relevance for 99% of the mathematics that humans do. And there are comparatively few problems in the mathematical mainstream where the so-called continuum hypothesis plays a critical role. In our class, we won't need to worry about it. It's not a question that will arise in this class. The part of the discussion that is crucial for us is this gap between countable and uncountable. There is a gap. That's all you need to know or care. So before going further with this, talking about this gap, it's worth stopping to point out why we should really care about the distinction between countable and uncountable. What's the deal about this? Beyond giving mathematicians something to talk about, what's the practical relevance? The person in whose mind infinite means only one thing will be skeptical on this point, and in the philosophical literature, certainly writers have been ridiculed for spending time, heated discussion about such meaningless and esoteric questions as how many angels can dance on the head of a pin. Well, that accusation is mostly unfounded. I don't think there's much documentation of people spending a lot of time on that, but as mathematicians, we have to be careful in the minds of students. The question of countable versus uncountable requires some justification as a topic of concern. So I like to approach this question by using examples from probability. I think that somehow most students accept that probability is relevant and useful to talk about. Probably all students in my class recognize that, for example, if you take a pair of dice, these are unbiased dice, the sum appearing on top is a number in the range from 2 to 12, where each of the outcomes appears with a probability as listed in this table. The least likely roll would be snake eyes or double sixes, so 2 1s or 2 6s. Each of those outcomes has probability 1 out of 36 on any given roll. The most likely outcome is for a total of 7, and that occurs with probability 6 over 36, which of course reduces to 1 over 6, but let's not reduce. That's not going to be helpful. You wouldn't be surprised to see that when you add up these probabilities, you get 1. Why is that? Well, it's because exactly one of these outcomes occurs. They don't overlap. There's no chance of getting two different values for the roll, and exactly one of them happens. This is all the possible outcomes that can occur. And the total probability for separate outcomes has to add up to 1 for mutually exclusive events that covers all the possible events that can occur. Now, let's switch to a different game. This one will have an infinite number of outcomes, so there's the main difference. So here I'll take a fair coin and see how many times we need to flip our coin before we get the first head to appear. Now there's a 50-50 chance that a head will already occur on the first toss, assuming the coin is unbiased. So that's probability 1/2. It may happen also that the first head appears on the second toss, meaning that you get a tail and then you get a head. This outcome occurs with probability 1/4. Or we might get tails, heads as our outcomes. The first head appearing on the third toss. And this would occur with probability 1/8. Or the first head might appear on the fourth toss with probability 1/16. The first head might appear on the fifth toss with probability 1/32. And so on. For each possible outcome, the laws of probability tell you what the probability is for the first head to appear on the nth toss, and the answer is 1/2 to the n. Now you might say, there's one other possibility, isn't there? You might flip the coin repeatedly without ever getting a head. And yes, there is no reason why this outcome cannot occur. In fact, if you were to continue flipping the coin an infinite number of times, every possible sequence of heads and tails can occur just as likely as any other. One of those is the possibility you could have tails forever, but the probability of each such outcome is 0. So I list that as the last entry in my table, but as probability 0. So yeah, it can happen, but it happens with probability 0. Our game, the way we designed it, stops if you get a head, and if you don't, then you just keep going forever with tails. Once again, if you add up all the probabilities, you do get 1. Because what we're summing is a geometric series. Well, plus one extra term, which, however, is 0. And again, there should be no surprise here, because the outcomes for the coin flips are mutually exclusive events, which account for all the possibilities that can happen. In the previous game, we had a finite number of possible outcomes. Here we have an infinite number of possible outcomes. And in both cases, the total probability over all outcomes is 1. No surprise. All right, now in our third mind experiment, we say we're going to measure the temperature tomorrow at a prescribed time and place. I'll say at 12 noon tomorrow. I'll say at the base of the flagpole in Prexy's pasture on our university campus. Everybody from my campus will know what I mean and where that is. And the probability that that temperature turns out to be exactly 50 degrees, that probability is 0. And of course, here I'm talking about 50 degrees exactly, not just to the nearest degree or anything. But of course, this is not a special feature of 50. You could pick any number. 10 times pi, that would be 31.415926 degrees. Temperature could be that, but the probability is exactly that is 0. For the same reason, and I can say for any real number, if you ask in advance, what's the probability the temperature will be exactly that number, then the answer should be 0. Now, if you add up the probabilities for all the separate events, you're adding up a bunch of zeros, which just gives you 0. And now the question is, why doesn't the total equal 1? After all, these are mutually exclusive events. The temperature is only going to be one thing. It has to be something. So when you add up the probabilities, you should get 1, and you don't. Now you can twist your head in knots, contemplate what's going wrong here. You can worry about predetermination or something, but actually the basic problem here is that the temperature ranges over some interval with an uncountable number of outcomes. And in the previous example, we had a countable number, either finite or countably infinite. And you know about infinite sums from second semester calculus, but I point out that when we define infinite series, the sums that we're talking about have an infinite number of terms, but only a countably infinite number. And it turns out there is really no meaningful way to talk about sums of an uncountable collection of numbers. It just doesn't mean anything, unless you have almost all of them are 0 or something. You're not going to get a meaningful number out of that. So if you believe that figuring out probabilities is useful and a valid use of mathematics, then I would compel you to believe that the distinction between countable and uncountable is a practical and important one. Now, this is an appropriate place to wrap up several loose ends in our discussion of set theory. The traditional approach to set theory, based on the Zermelo-Fraenkel axiom, starts with the empty set. This is where all our set theory starts. All the axioms allow us to recursively build up more and more complicated sets using various operations like taking unions, intersections, Cartesian products, etc. Everything starts with the empty set, which is the set having cardinality 0. And by the way, it's unique. There's only one set with no elements. Actually, this fact is enshrined in the axioms. The symbol, by the way, for the empty set is a circle with a line through it. It's not a letter O with a slash or a 0 with a slash through it. It's not a Greek letter phi, lowercase phi. It's not a Norwegian vowel. It's a symbol unto itself. Actually, several years ago, the computer science textbooks used to use a 0 with a slash through it to represent 0, so that people would not confuse it with the letter O. They would say it's 0. And nowadays, people have appropriated for other things as well. I think that convention is out of fashion now, but the symbol for empty set in any case is different from that. Every set S has the empty set as a subset. I'm saying as a subset, not as an element. So I hope a few examples will give you some practice with the notation of elementary set theory. Let S be any set. The power set of S is the collection of all the subsets of S. And we'll denote that as script P of S. And this is a set that is guaranteed to exist by the Zermelo-Fraenkel axioms. It is the set of all subsets of S. This is our most important way of recursively building new sets from old. For example, consider this set 0, 1, 2. It has 3 elements, 0, 1, and 2. It has 8 subsets, and they're all listed here. So the power set is a set of sets. The placement of the brace brackets is important here. It's all important, so be careful. When I say important, I can say that in some sense all of modern mathematics, via Zermelo-Fraenkel set theory, depends on being careful about where you put the brackets. That's what it all comes down to, all of mathematics in some sense. You should immediately pick up on the fact that a set with 3 elements has exactly 8 subsets. So if S has cardinality 3, then the power set of S has cardinality 8, which is 2 cubed. Now let's back up and do a smaller example. Here is a set with 2 elements. It has exactly 4 subsets. So the power set has cardinality 4, which is 2 squared. Now, the even smaller cases, if S has 1 element or even 0 elements. When S is a singleton set, meaning it has 1 element, then it has two subsets, the empty set and itself. So for a set with cardinality 1, its power set has cardinality 2, which equals 2 to the power 1. And if S has no elements, then it has to be the empty set. In this case, the power set is just a singleton, which is the set of the empty set. That's only one element in the power set. A 1 equals 2 to the 0. Now you get the idea. If a set S has n elements, then it has 2 to the n subsets, meaning its power set has cardinality 2 to the n. The proof is easy. I'm not going to prove it yet. Do that in a later video. In general, take any set S. The power set of S is the collection of all subsets of S, denoted script P of S. The axioms tell you start with the empty set and take more and more power sets, and then subsets of those, and in some sense this is giving you the entire universe of sets from the Zermelo-Fraenkel set theory point of view. It's called the von Neumann universe of sets. It's the arena of the sets that we live in. For every set S, the cardinality of its power set is denoted 2 to the power of the cardinality of S. You could call it a theorem, but unless you really know how to define exponentiation, what would you use to prove this? So we could take this as a definition in the case of infinite sets. And in the case of finite sets, it's a theorem. Until you learn about exponentiation in general. But here is a theorem. And of all the things that Cantor proved, this is the one that most deserves to be called Cantor's theorem. It's more general than the earlier theorem of Cantor that we gave. It says that for any set S, the power set of S has cardinality strictly larger than the cardinality of the original set S. The proof is not hard, as we'll see in a moment. But first, let's look at this consequence that we can start with the natural numbers, the countable infinite set, and then take the power set of that, the power set of that, the power set of that, and keep going more and more rungs up the ladder. This is not even getting near the really big ones. Our name for the first level in this hierarchy is Aleph 0. That's the cardinality of the countable. And the next level here in this list is the cardinality of the reals. And we denote that, therefore, by 2 to the Aleph 0. And the next one would be 2 to the Aleph 0, and so on. There are other nicknames for these cardinalities, but this will do just fine. And turning then to a proof of Cantor's theorem. Before showing strict inequality, let's show less than or equal to. So we have the size of the set S is less than or equal to the size of the power set just by mapping each element of S to the singleton set, brace brackets A, which is a subset of the power set. And this map is 1 to 1. So it shows that the size of the power set is at least as big as the size of the original set S. No surprise. How do you show strict less than? Well, you have to show that there's no bijection. We'll do that by contradiction. Suppose that there is a bijection, F, from S to its power set. We need to find a contradiction from this. To do that, let's define the following set that I'll call capital A. It's a subset of S. It's defined as the set of all little a, such that little a is not contained in F of little a. Now this is reminiscent maybe of Russell's paradox, but actually Russell got the idea from Cantor, so that was the original proof that used this idea. This is just another application of Cantor's diagonal trick. I can explain where the name comes from, but maybe now is not the time to digress about that. By assumption, F is bijective, and it's certainly onto, so our set A, which is a subset of S, has got to be F of some element little s. Now we can ask the question, does little s belong as an element of capital A? Yes or no? Well, if S is in capital A, then by definition of our subset, S is not an element of f of S, and that's a contradiction. On the other hand, S not being an element of A, which is f of S, means that S is in the set capital A. And that's, again, a contradiction either way. Now, there's a difference here between a proof by contradiction, like the one we just did, and Russell's paradox, which gives a contradiction in the entire mathematical system in which we're working. In this proof and other proofs by contradiction, the proof only gives a contradiction that derives from some faulty assumption. In this case, the contradiction derived from the apparently faulty assumption that there was a bijection F. And we just showed, therefore, by contradiction that there isn't any such bijection. In Russell's paradox, there was no way out. It just came straight from the axioms to a contradiction. So that's the difference in a proof by contradiction. It's not really a paradox in mathematics. Now, there's a little more to be said about the language of sets. Informally, people often use terms set, class, collection, and family interchangeably. Russell's paradox shows that we need to be careful about talking about such things, so we will reserve the term set for something constructed using the rules of ZFC. Still, there are times when, informally at least, we want to talk about a family of things that are too big to form a set. We can't call it a set in the strict sense. And then we use the language of a class. In particular, we talk about the class of all sets. Another thing to note here is there is no largest set, and it follows from Cantor's theorem. No matter how large a set is, its power set is still larger. And as a consequence, there cannot actually be a set containing all sets. So we talk about the class of all sets, but not the set of all sets. So a stronger statement than what I'm saying here is that no set can be an element of itself. That's a strictly stronger statement. So instead of a set of all sets, we have the class of all sets. This is an example of a class, and some other examples of classes in the strict sense. We have a class of all vector spaces. That's too big to be a set. The class of all fields, etc. Not giving you a proper definition here of what a class is, but I guess I didn't really define fully what a set is anyway. But you can think of a class as being something a little bit more general than a set. And a class which is not truly a set is then called a proper class. And it's perhaps lamentable that mathematicians take so many ordinary words and reserve them for special meaning, and then you can't use it for anything else. So if you just want an ordinary word that mathematicians haven't already appropriated for a collection, you can say collection or family. Those are probably pretty safe generic words that you can use.